So welcome back, everybody. The topic today is to discuss these resampling methods and statistical interpretation of the results which we are ending up with. And there are some basic assumptions which are made about the model we have. And we are going to use these basic assumptions together with a famous theorem in statistics, which is called Bayes' theorem. And I guess that most of you have heard about this theorem, but you may not have applied it. And Bayes' theorem is an extremely powerful theorem, and you could think of that as almost as Pythagoras in geometry. So the topic which we're going to look at first is basic statistics and Bayes' theorem, and how we can derive things like ridge regression and lasso regression using a statistical interpretation. And when we are done with that, we are going to dive into resampling techniques. And resampling techniques play a very important role in order for us to narrow down the statistical deviations in the parameters which we define, but also in the quantities which we calculate, like a mean value, like the variance, or the mean squared error if we are dealing with regression calculations, where the mean squared error serves as a kind of gauge to estimate the quality of the model which we have defined. So let me just switch to the Jupyter, no, to the whiteboard immediately, because I wanted to set up some of the basic quantities which we are going to look at. Let me just take this down here. So the main topic today is a statistical interpretation or statistical derivation. Just let's call this statistical interpretations or data analysis and resampling techniques. So many of the examples I've showed you, these are data sets which we normally call vanilla data sets, because they are data sets for simple functions, and we can regenerate and generate as much data as we want all the time. However, when you run an experiment, you have the data, and that data you have are the data you have to live with. And if you have 1,000 data points, that is probably what you will have to live with. And then the problem is that since this is a sample of data, when you calculate the expectation values, you're calculating the sample mean. And the sample mean may not be the same as the true mean if you were to know the probability distribution. So let me just repeat some of these techniques, because these two things we are going to do are a little bit interfaced with each other. And with the resampling techniques, what we want to is to get a reliable estimate of, let's say, the mean squared error or the mean value or the variance of the quantities which we are looking at. So what we have assumed is that we have a data set y as a function of x, and now y can be a vector and x can be a vector, which are described by a function f of x, which we assume is a continuous function, but this is a non-deterministic, it's a deterministic function. So there's nothing stochastic about it. And then we have some normal distributed noise. So this is just to remind you quickly of what we discussed in the beginning. So this function follows a normal distribution with mean value and a variance sigma. And then we have assumed that f of x is a deterministic function, a continuous and deterministic function. And then we have a data set, D, the domain of data, and that has a set of input variables, y, and outputs or targets, many different names for the same quantities, up to some x of n minus 1 or y of n minus 1. And what we end up calculating now is typically mean values and variances and mean squared errors. And these are expectation values. So ideally, there is a distribution behind x, and there is a distribution behind y, but we don't know them. Ideally, we have a probability, a distribution function, PDF, P of x, there could be a P of y, etc. This is the ideal. So if you then calculate the mean value of y, so we would have a mean value, the expectation value of this variable y, would then be given by an integral of a P of y, y of dy, and this is integrated over the domain of variables y. So this is the ideal. And if it's a discrete probability distribution, this will be given by a P of y of I multiplied with a y of I, and we would sum over all the i's which are represented in the domain D. This is in case we have a discrete probability. And the same applies to the variance, the covariance, and any other quantity we calculate. So we would have a quantity like the variance. So let me just repeat these quantities. The variance of y would then be given by an integral, and then we still have P of y, and we have y of I. We often label this with a mu of y minus mu of y squared. We could have the covariance of two variables, and let's just call this y and y tilde. So this would now be given by the probability, if that exists, of y and y tilde. And then we have y minus y mu tilde, no, sorry, multiplied with y tilde minus mu of y tilde. And then we have a dy tilde. And we discussed in the beginning of the semester or the course here that in case these are independent and identically distributed variables, then the covariance is equal to 0. Then what we have been calculating, however, are sample means. So we have to distinguish between the sample mean and the true mean value. So this is our reality. So the sample mean, which I'm now going to put in terms of a bar here, that is simply given by the sum over n, and then I have a sum from n minus 1, and then I would have my y of I here. And then we would have the sample variance. And this is not the same as the true value if we know the probability distribution behind these variables. And then we would have the sample variance, which would then be a var of this y, and then we put a bar on top of it, just to indicate that this is, and now I'm going to assume that this is an unbiased. If it's biased, you would have n minus 1. And this is a sum, and this is given by y of I minus this y of y bar squared. And this is also different from var of sigma squared of y here, which we defined earlier. So ideally, you can show you have this strong law of large numbers. You also have the weak law of large numbers, which all these theorems state that in the limit where n goes to infinity, you should approach the true value. However, many data sets which you encounter are data sets with a few hundred samples, which means that what we are limited to do then is actually to calculate the sample mean and the sample variance. You will also see these quantities being written in terms of like this expectation value. So when we look at the sample mean, we wrote this previously for the true mean value, but we will also see that written out in terms of the sample mean, etc. Not only the sample mean, but also the variance of the mean, the covariance of the mean, and also the mean squared error, which we have seen before, is also considered as an expectation value of y minus our model tilde squared. and that's given by 1 over n, and then we have a I equals 0 to n minus 1, and then we have y of I minus y of I tilde squared. So that would be the sample mean value. Now, one of the things we want to do with the resampling techniques is to be able to evaluate this quantity here in the most reliable way. And these resampling techniques like cross-validation and Bootstrap are techniques which allow us to actually do that. And that's very important because then we can give a better estimate of the mean values or the sample mean or the mean squared error. So typically with these resampling techniques, so let me give you the kind of overarching message here, and then we're going to dive into the details afterwards. So the typical techniques which are widely used is the Bootstrap. That's often used on independent and identically distributed variables, and it's often applied to cases where you have few data points. And then the other one, which is perhaps more used in machine learning, is cross-validation. That's the perhaps the most popular one. And both of these techniques are very simple to implement, as we will see. They rely both on the central limit theorem, and we will see demonstrations of that later. But if you now think of the calculation of the mean squared error, so let's look at the mean squared error as an example. That MSE as example. And one of the things which we end up with then is to calculate the mean squared error for the test data and the train data. So a typical plot which we will make is a plot which looks like this. So we're going to calculate the mean squared error as a function of the model complexity. If you do a polynomial fit, the model complexity would be the degree of the polynomial you fit. So for every model complexity, you compute a mean squared error for the training data, and then you compute a mean squared error for the test data. So we split the data in training and test. And typically what you would see then is something like this. So you would have a large mean squared error. And for the training data, you can actually, we're going to put this mean squared error for train. What you will see then is that this curve is something which we can perfect with the better and better model or higher and higher model complexity. So you can really make a model which fits every single data point you train. And that means that your mean squared error is going to be smaller and smaller and smaller. However, if you have fitted this so nice to the data, when you now apply it to some test data, which was not in the training, then you can fail miserably. And this is the typical case which we normally call overfitting. So the mean squared error of the training is perhaps a boring quantity. The mean squared error applied to the test data, which was not included, is the quantity of interest. And this is a quantity which in the first project, you're actually going to play around a little bit with. So if you look at the test data, you would then have something which goes like this, and then suddenly it starts increasing. So this would be the MSE for the test data. And what you would have here would be the optimal model for that specific data set. This will change from data set to data set. So it's not given that if you now increase the number of data points that it will behave the same way. So this will be your optimal model. And this case here is normally called the overfitting case. Now, this will be a calculation with just only one run for the mean squared error. So with the resampling techniques, the whole idea now is to be able to narrow down a region where you have so that you can get a better estimate for the mean squared error. So let's look at what happens when we do this with a resampling method. So let's keep this model complexity here. And let us stay with the mean squared error, because that's often, from a pedagogical point of view, that is pretty easy to plot and to test. So this is the mean squared error on the test data. So what you could do now is to use a data set, and you calculate the mean squared error as the sample mean squared error. So keep in mind now that we do not have the probability distribution. That's one of the typical paths in standard machine learning, that you don't have the PDF. You may not be interested in the PDF. In reality, you are interested in the PDF. But in standard machine learning, you're just calculating sample means, and you're looking after predictions you can make based on that, on test data, and to find correlations in the data. But you cannot estimate properly the error. You can, with this kind of approach, you can actually try to extract a probability distribution, and with a probability distribution, you can find the error in your mean squared error. But suppose now that we run this calculation here, and now we produce a mean squared error for test, which goes like this. So, and let's label this as data set 1. So this is D1, and I'm going to come back to what D1 is. Then I can use a new data set. So what I'm going to do is something which is called bootstrapping here. Have you heard about the bootstrapping method? So bootstrapping means that you reshuffle your data, or rather you pick randomly in a data set. So we have an original data set here, this set here, and then you calculate the first mean squared error on the test is done on this data set. Next time, you pick randomly points in this data set, but you do that n times with replacement, which means that you can pick the same data point several times. This is your new data set. And now you call this D2. And then you calculate the mean squared error with D2. So every time you resample it, you also train it again. And you produce a new test with the trained model, but on the same test data. So keep in mind the test data stays the same. So when you have split your data into train and test, the test data stays in the vault and you don't touch it. So now you resample your training data, and you produce in reality a new model. And then when you have trained this new model on data set D2, you calculate the mean squared error for the test. You see the basic recipe here? Then I produce a new training data set D3, and then a D4, and so on and so on. And every time I compute a new mean squared error, or a mean value, or variance. Depends on the quantity you want to calculate, okay? So that means that now I train a new data set by just picking randomly in the training set. So I've made from the very beginning, I split my data in train and test. So now I produce a new data set, and let's give this an orange color, and that could look similar like this, but then it may look something like this. So this would be D2. And now I repeat this again and again. This is actually Bootstrap. So now I produce a new data set, and it could be something like this. So this gives me a new mean squared error, D3. And then I can continue and do this bootstrapping or resampling as many times as I want. This means that you now have a band of values. And this band of values lies, let's say, within this region. So what you do then at the end is that you take the mean value of all these mean squared errors, and that's the quantity you would present as your best estimate of the mean squared error. And you can also then calculate the deviation from this mean value based on the mean squared test errors you have calculated. So I'm going to write down with words the basic philosophy here. So at the end, you could now think that we have a curve which looks like this. So suppose this is the curve here, this one, and this is the mean mean test error of all the resample data. And with that, you can also calculate now a standard deviation for these mean squared errors. So you can then say that my standard deviation may be something like this from that mean value. So it's a cheap way of generating new data and then simply train a model on the new data, use that trained model on the test data you have, and then just keep repeating this till you have a mean squared error you think should be the best representation. So let me just write down the basic steps in Bootstrap. So Bootstrap is one of the resampling methods. So the first, you require, obviously, that you have a domain of data, D, which is now this data set, x0, y0, up to xn minus 1 and yn minus 1. And let's just make this, we're going to simplify this and just assume that we are interested in the x values. So instead of having x and y outputs and targets, inputs and targets, we are going to just look at when we are setting up the algorithm just in one variable. Then what we do then is to split in trained and test data. So we do that before we start doing any resampling. Then what we do next is that we define or we require a variable m, which is the number of resamplings or bootstraps, in this case, number of bootstraps, bootstrap samples. So we have now a trained set. So we have defined a D train, the domain for training, and D test. So it could be a split of 80% for training and 20% for test. But the point now is that the test data is just kept in a vault and it's not used in any of the resamplings. So the test data stays the same all the time. That's the whole thing with the test data. It should be untouched. So you can do as many trainings of models as you want, but what you're doing now is that you leave the test data as something which none of the model sees in the training. Then what we do now is we have a for I equal 1 up to m. And now we now make a new train set. So make new D test, or sorry, D train. And let's call this as a function of I here. By randomly selecting with replacement. So let me have in here a small example just to exemplify what we are doing. So suppose your D train looks like this, the original one. And that's given by data points 1, 2, 3, 4, and 5. Your new D train is this asterisk D train. And that could now be, we pick now number 2, that's the first point. And then we pick number 3 here. But then we could pick number 2 again. We could pick number 4 randomly. And we could pick number 1. That's my new data set. And so I would treat this as a new data set. And you can actually show there's a proof for the Bootstrap theorem. So the Bootstrap theorem is actually, when the method was proposed by Efron in 79, this was just proposed as a variant of a popular method, which was called a jackknife method, which also had not been proven properly statistically. So what Efron proved later, after he presented the paper, was that this is a way of resampling which converges to the true value of, let's say, the mean value, the variance, if you then do this repeatedly many, many times. So you can show that this is actually something which will converge for independent and identically distributed numbers to the true expectation value. It will depend, when you do this numerically, on the data you have. In the slides and the Jupyter notebooks, there are actual examples which we will go through a little bit later. So in this case, this will now give us a new data set. So when I say picking with replacement, is that you will select again among the same numbers, and you can select the same number several times. Then when you do this, next, what you do is you calculate or you train the model. So let me just do that. So that's the next step. So train model. I. And with that model, then you compute expectation values. And the quantity we are looking at is, for instance, the mean squared error. So in this specific case, we will then compute the mean squared error. Sorry, MSE. For this iteration, I. And then what you can do next, so this is on train data, on train. And MSE on the test data. So it's always useful to see how well this model is doing on the training data as well. But at the end, what we are interested in is the MSE on the test data. So the test data is not included in the training because the training was based on the data set, which you see here. This will be our training set. Then we train a new model, and then we apply that one when we've done it to the MSE test. And then you continue till you have reached the last point. So end loop. And the final thing is actually to compute the MSE for the test data as a function of 1 over this number of bootstraps which we have made up to m. And then we would simply sum from I equals 0 up to m minus 1. And then we simply take the average of all these cases which we have tabulated. And that is going to be an average of all these mean squared errors. And with this quantity, you can also calculate then, when you have these quantities, you can think of calculating the variance which you have here and the standard deviation, so that when you go back to the image, the figure which we put up here, you could then find the deviations, obviously, for the different samples you made. And clearly, if you have a very large scatter here, that may perhaps mean that you should rethink how much data you have for training and testing and how many bootstrap samples you make. But this is essentially the bootstrap method. And this is the way it was presented by Efron in the original paper. And then there is a wealth of statistics, literature in statistics, where you actually analyze this method for independent and identical distributed events, for non-independent, and et cetera, et cetera. So we are just going to use it. So I'm not going to go through the theorem. Yeah.
How do you choose M?
So this is something you have to play around with. And many people often choose M equal to the number of data you have. But you can have it smaller, because this quickly becomes computational intensive if you have a huge data set. So this is all up to you. So these are parameters you would play around with. The thing you would want to reduce is actually the scatter, which you see here. So you would like now, when you compute these different data sets, you would like to not have a too large a spread, because that means that probably you have too little data here. Yeah.
Sorry, because I think you told me that in this case, for each new data set, training data set, you're computing new parameters for the model, or are you updating the?
No, you're computing. You're training a new model every time. So you train the model with that specific data set.
From scratch.
Yeah, from scratch.
So if you get, I understand that if you get height variance between each training data set, it can be also overfitting, maybe.
That can also happen. So it's very useful when you play around with it to look at different. Obviously, the way you train, you split your data and train and test. So the more data you have on training, normally the better it does. But this can again vary on the quality of data you have. If you have many outliers and you use the mean squared error, which is sensitive to outliers, that can clearly give a large scatter in the mean squared errors. So everything you see here is dependent on your data. The kind of wisdom you can extract is that the more data you have, the better behaved these curves will look like. So all these methods of data greedy. Oscar?
You always keep the training data set the same size for each bootstrap equation.
Yeah, because you have made the split before you do the bootstrap. Yeah. So that means that, and then this is something you can play around with. So you can redo everything with a new split between train and test. And what is commonly done, like many of these functions which split your data, they split it randomly. So every time you call a train test split with scikit-learn as a library, it will reshuffle your data randomly. So that's also something to think of. So it's not that you do training the first 80% and test the next 20%, but it will typically reshuffle your data.
So all of this is for a given model.
Yes. And then you have to redo this for the different models. So you see, there's a lot of how to say, practicing. And in the first project, I thought that you could actually practice with these things. I think it's important to do it because it gives you a feeling of the sensitivity of the results on the amount of data you have. So everything here will actually depend on the data set. Yeah.
Then which model do you choose to run with the
so you
said that we trained it, like in this case, we trained n different models.
That's a good point.
Why do we do this thing to choose the best one, or just to see how our model in general is good? So
that's,
there is not that much difference. That means that any data set that I can choose, it's quite good.
Exactly. That's what you would end up doing. Yeah. So when you have cross-valid, or when you've done this bootstrap, you would then see if you have a very small scatter, you would say that I could choose any one of these. But this is more just to give an estimate of the mean squared error, because when you have something like this, the what you want to give the user of the model would be an estimate of the mean squared error, because this is something you will always tabulate. What is your accuracy score, your score, right? So how well does the model do? That's a very important aspect of it. And that's why you do this kind of bootstrapping or resampling techniques. And then you could typically conclude that, like in this specific case, suppose now that you see that you start overfitting here, then what you would say is the following. Okay, I'm overfitting here. That means that my best model is this one. And within this model, I have estimated the mean squared error to have this value. But then you could take almost any one as long as this scatter is very small. Yeah.
Instead of keeping this data, if you can change terrain from separation by separating the different parts. Also go ahead.
I don't think, could you repeat the reasoning?
I mean, instead of keeping the base data same,
yeah,
we can change each time for each training.
Yeah.
As it from the beginning.
So
without seeing the data every time.
So what you're saying is that every time you do a bootstrap, you produce a new test set. Is that it? But then the test set, because the whole idea with the test set, that should be something which is unseen. And it should be the same for all the models you train. So what happens now is that it will be different for every model you train. And that would defy the whole thing with the test set. That's true. So I say what I showed you here is a standard path where you simply just take out a data set from the very beginning, and that is never seen by any of your training. So what you will also have, and this goes back to a little bit what Chiara asked, is that you would find that it's common to split the data in training, validation, and then test. So that means that in this specific case, you would have a test data which is never touched. But every time you do this kind of bootstrap, you would actually split the data in just training and a test set, which is a validation set, where you refine the model so you have the best parameter for that specific model. And that would follow what you're saying. So you would always leave out a test set, which is never touched, but a validation set, which is then used to test the training model and say that these are the best parameter for this specific model complexity. So that's pretty common to do, actually. And you will see that in textbooks, that you split the data in training, validation, test. But that, again, depends on how much data you have. So if you have 1,000 data points, then you don't have that much flexibility. So remember that all these methods which we are dealing with are data greedy. The more data you can feed in, the happier the methods are. So, yeah.
Of course, in these models that we are working with, it's very important when you're training the model, the position on the data, on the input already.
Yeah.
Because if you change it, the model, each beta parameter change, can change a lot. So I understand that it's like the basis of this. That if you are making data with each resample, new data sets, and you're repeating points, for example, in the second one you have drawn with 2, 3, 2.
Yeah.
It cannot be a problem if you repeat a lot of points on the same, because then you are losing generality.
Oh yeah. So this again depends on how much data you have. So if you have a very small case like this one, then this will be a problem. Clearly, you can actually show that you're going to converge to roughly 66, 70, 67% of the correct value typically. That's the in the proof of effort for the Bootstrap model. I just wanted to bring up another way of doing this resampling, which is the one which is more used in the literature and in analysis, which is called cross-validation. So Bootstrap is widely used in many applications, but typically in machine learning, the method which many people tend to use is cross-validation. So let's just do that, and then we take a break, if that's okay with everybody. So the basic idea is very simple to explain. So you can now decide whether you want to do splitting into training, validation, and test. But let's just stay with the train and test. So what you would define is something which is called number of folds, which I'm going to give it a variable k. So this becomes a parameter. When you define the number of folds, what you do now, so let's do as an example, k equal to 5. So I would have my domain of data, which are now split in 5 different slots, equally sized. 1, 2, 3, 4, and 5. And then I would say that I could use, so I'm going to use colors now. So if I use the, there we are. So I'm going to use the color blue T for train. And I'm going to use red for test. So I could say now that slot 5 is the one which is used for testing. And then I train a model with the data which we have here. Next, so this will be my D1. Then I do a D2 here, where I now simply change these different assignments. And I just do the training. I could have train here, train, train, and train. And this one, the next one becomes my test set. And then you see the pattern here, D3. So let me just make the boxes here. And then I do a D4. And then I have my D5. So I would have this as test, test. And now I could have this as test and test. Then I have test. Oh, sorry, train. And in each case, what I do now is that I calculate the MSE. This is 1 for test, on the test data. Here I calculate the MSE 2 on the test data. And I do this all the way down to the MSE for the 5th set. And I calculate my test data. Then the final mean squared error on the test data is then simply 1 divided by k, which we put to 5 in this case, equals 0 up to k minus 1. And then we have the MSE test as a function of this I here. And this is the mean squared error, which we would present as the final mean squared error. So this is cross-validation. In this case, and this goes back a little bit to what Ali said, the test set will change. However, what you could do, which many people actually do, and again, it depends on the data set, you would split this in training, validation, and then the test, which you have in here, becomes your validation set, where you pick the best possible model for that data set. And then at the end, you have trained a model which you think is the best one with these 5 folds. And then you apply this to the final test data, which is just kept outside of everything. So this, in this specific case, we keep changing the test data. So just keep that in mind. That's just a slightly different way of doing it. But you could split the data into training, validation, and test, and then do the k-fold machinery or the cross-validation machinery on the training and validation set. So you validate a model which you think is the best possible model for this specific splitting of your data. And then you feed that one into the test data and calculate a mean squared error. So the idea here is actually to extract some averages, which you hope are averages which represent the true averages. We don't know that. This is the problem we have to live with when we do machine learning, is that we don't know the probability distribution behind the data which we have. So the ideal would obviously be that somebody gave you the probability distribution. But in general, we don't have it. So these two methods are the standard methods for resampling data and produce a better estimate or a more narrow down of the mean squared error, the quantities you want to calculate, so that you can actually estimate what is the error on your mean squared error which you compute. This is essentially what you want, is something like this here, and where you can present to the reader the best possible mean squared error, and with a as narrow as possible the spread in the error. Now, you see now that this k-fold, or the number of folds, becomes a parameter. And it's not given that you would get the best result with k equal to 5. So most practitioners deal with k between 5 to 10. You could run a case where k is equal to n minus 1, so that your test data is just one data point. This is called leave one out cross-validation. That becomes expensive, because then you would do the cross-validation for n minus 1 data points. So if you have 10,000 data points, you would do this 9,999 times. And that becomes time consuming. So everything we do here contains a level of pragmatism, where you try to strike a balance between the number of cycles and the time you're willing to wait and spend, and the accuracy of the results. Yeah?
A question about, I think you told at the beginning, with respect, for example, can you scroll down? Or other, for example, the K.
Yeah.
You told that if the data is by with bias, we should use the correction of
k minus 1. Yeah, yeah.
But if you're working with data,
yeah,
you can know some of that.
Yeah, exactly.
So do we usually use the correction?
Yeah, that's if you use libraries like scikit-learn, and if you use NumPy's function which calculates the variance and the covariance, that is always assuming that you're doing a sample expectation value, and that contains the correction n minus 1. And you will see that quickly. If you calculate the variance and you divide by 1 over n and compare with what NumPy gives you, you will differ. So I just do it because I didn't put an assumption on the data. And in textbooks, you will often see that it's just written like this. Yeah.
So would you in this case also use k minus
1? Yeah, you would use a k minus 1. Yeah, yeah. Yeah.
Another question, like especially if you have a small data set,
yeah,
you will probably like use data augmentation. So
yeah,
there will be some randomness in the data anyway.
Yeah.
So how do you deal with it, or you just ignore it and say like we split it in 5 times and assume it's about the same every time?
So the easiest answer is actually you just ignore it, which is what many practitioners do. But clearly you can actually start looking at more refined methods for doing that. And typically here, what is often done is actually to bring in some Bayesian statistics and try to find a probability distribution, because then you can actually calculate error estimates in a much better way. And that's going to be the topic after the break. So I just wanted to go through the basics. So there's nothing more hidden unless we want to dive into the proofs of, let's say, the Bootstrap method, which I actually want to avoid because that would take easily 2 to 3 sessions to go through it. Should we take a small break? I went a little bit over time, but I just wanted to conclude the basics of the resampling methods. Okay, let's put the... So the thing which I wanted to discuss now, after we presented these methods, is to go back to the statistical interpretations of the standard regression methods. So in general, when you look at machine learning, the standard approach has been what in the statistical literature is called the frequentist approach. So you're more interested in the frequency of the data, and you're less interested in extracting a probability distribution. You can do that with these methods, but it's normally in machine learning, as we mentioned, we are more interested in fitting a model and then make a prediction based on that. And we are less interested in estimating the errors. And we are also interested in correlations. So correlations are typical quantities you would get from the correlation matrix. So what we are trying to follow is the standard path. That means also that when we come towards the end of the semester, when Anders Kvellestad is going to present things like Gaussian processes, then topics like Bayes' theorem are going to come back again. And then we will try to develop probability distribution which define or which describe the data. And that leads to normally what's called Bayesian statistics. And there is a whole field which is called Bayesian modeling determination, Bayesian machine learning, and so on and so on. So when you do a Bayesian machine learning approach, the benefit is that you actually get a probability distribution. Depends on what's normally called your prior. However, the thing is that it's off with a Bayesian approach, it becomes computationally more expensive. And there's always this balance between the number of cycles you're willing to invest and the type of results you want. However, I'd say that doing both estimation of errors and finding causations, because with a probability distribution, you can say, what is the likelihood of B given A? And to make predictions, that means to fit a model and to find correlations in the data set. This is actually what we, in many cases, want. So machine learning has, in a way, what you might call the standard approach, in particular, the one which deals with image recognition. It has put less weight on this kind of type of information. However, for many of you in your thesis projects, this is actually going to be the more interesting part. So we will try to compensate for this kind of more machine-like machine learning standard approach with the introduction of a Bayesian approach with Gaussian processes towards the end of the course. So for many of, as I said, in many of your thesis projects, the extracting a probability distribution is often more interesting. That's the case in my own research when I use machine learning on quantum mechanical systems. And also what we call physically driven input to the machine learning methods is something which many of you may actually end up looking at. So now we are just trying to keep the kind of path which is outlined in most textbooks. However, it's useful to see the statistical approach, and this is what we are going to do now, because these things get mixed in again and again. And sometimes you don't see the wood for the trees, because, I mean, sometimes people speak in a statistical language, and other times you just speak in terms of a machine learning language. And so then you may ask yourself, what's the difference? And how should I use this? So let me try to baby step you now through some of these ingredients. So perhaps not that one, but this one. So let's look at statistics. So the way I'm setting up this course is actually to bring in the elements when we need them. It means that this is not a coherent course on statistics and probability theory. So I'm just bringing in concepts. And I hope that you can reboot your memories and then remember back and spool back and try to just remember what you learned about statistics. Often the problem with many bachelor programs now in science now, all over Europe, is that statistics get squeezed out and you just scatter the needed statistics in this and this course. And then people never get this kind of coherent understanding of the basic concepts. So one of the things which we mentioned, we are going to calculate the expectation values. And we have assumed that our y, so let's just start with one example, yx of I, which we wrote as y of I, is now given as this function fx of I plus this epsilon of I. So if I calculate the expectation value of that quantity, and let's now just write it like this, of y of I, this is going to be the expectation value of this function f of x of I, and we don't know that function actually, but we are making a model for it. And then we have the expectation value of this quantity epsilon of I, right? And we have already decided what the value of that one should be, right? We have decided that that has a mean value equal to 0 by definition. So this is a normally distributed noise with a variance sigma squared and mean value equal to 0. That's a pretty standard approximation. Then the question is, what should this one look like? So what we have done is actually to make a model with x of I, and we have approximated that with a linear model in the unknown parameters beta. So we would have a sum up to the number of parameters we have. And then we have the matrix elements of the design matrix. So this is xj of beta j, right? This is just a number, right? It's a scalar, the way we have replaced it. We have also assumed that f is a deterministic function. So the expectation value of a deterministic function, which is just a number, is just that number, right? So that means that the expectation value which we have here, we actually wrote this in a more compact way, like this x of I, and then we had the bar here, no, this star, like this. This is a kind of more compact notation. So it means that the expectation value of y is actually given by this sum here. This is just a scalar, just a number. And x is fully deterministic. And we also assume that this beta has as its own expectation value, beta. And we are going to show that pretty soon, or rather, I'm just going to give you the result, and I'm going to give that as a small exercise. So what you can do next is to calculate the expectation value, or the variance. So if I calculate the variance, and I'm going to leave that as an exercise for you guys, and I'm just going to write this. So that means that the expectation value of y itself is just given by x times this beta, because the mean value is 0. What you can also show, and this is, I'm going to leave this as an exercise, and you will get that exercise back in the project, number 1, which we can discuss in that week of December the 12th to the 14th, when we meet again, because then I thought of presenting the project and wrap up the final elements which we need for the project. So you can show that this is actually given by this variance of the epsilons. So this is the same as the variance of this parameter epsilon. Sorry, not sigma, but these epsilons. You can also show that the expectation value of the parameter beta is actually equal to beta. So we normally say that then it's an unbiased statistical parameter. We don't know the distribution of the betas. However, what this says is now that the y of I, or y, has mean value x times beta and variance sigma squared. Now, since x is deterministic, what we can assume now, and this is an assumption we make, is that y follows a normal distribution, since epsilon follows a normal distribution. So this is an assumption we are making. So what we could say now is that y follows now a normal distribution. Well, actually, it's a Gaussian now because we have a mean value which is different from 0, with a mean value x times beta. So if we write it like this, it means that every single y of I follows now a distribution where we have this mean value and sigma squared, which is nothing but 1 divided, if we now take the full expression, of 2 pi sigma squared of e to the minus, and then we have y of I minus this Corny notation, which I put up here, divided by 2 of sigma squared. So we infer that from the distribution of the noise which we have. So we've said that x is a deterministic variable. What we can assume now is that beta is a deterministic variable, but later we will change this when we look at ridge and lasso regression. So these are just assumptions we are making. So we cannot prove, but we are inferring from the noise which we have assumed to be normally distributed. Okay? Now what we can do next is actually to derive ordinary least squares using this distribution. So this is now the probability of finding y with a given value of beta and a given value of x. We are now going to make a new assumption. And then we are going to assume that the y of i's are what we call independent I and identically distributed. And you've probably seen this shorthand in statistics textbooks. IID, independent variables and identically distributed. So every y of I has the same distribution. And they are identical, which means that the total probability is just the product of the individual probabilities. Is that something you're familiar with, heard before? The many heads nodding, and there are some blank faces. So the majority is nodding, so I'm going to take that. So this is just some basics. So that means that what I'm going to describe now is a probability, and this is a probability for the domain D given a variable beta. And this is going to be given by the product, since these are independently distributed from I equals 0 to n minus 1. And then I have all the individual guys, this P of y of I. And I'm gonna skip x, if that's okay, just for notational simplicity, with a given value of beta, like this. And this P of y with given beta is now given by this model which we have made. So this is now my probability. And now I'm asking the question, when you look at the probability, are you interested in a parameter beta which minimizes the probability or maximizes the probability? What would you prefer? If I make a model which minimizes the probability, is that something you would bring to your friends and say, this is the one you should use? It minimizes the probability for you finding a specific result. No. So we want to have a parameter beta which maximizes the probability. So that means that what we want now is to find an optimal beta which maximizes this probability of beta in the domain of these P's, and then take the P of the whole domain of data as a function of beta. So this bar means what is the probability of finding the domain D, where the Y's are the outputs, with a given beta. So we want to maximize. Now, the problem we have now is that if we want to take the derivative of this quantity, yeah, go ahead.
Just go.
Yeah.
You write yi is proportional or is equal to e to the power of something yi.
Yeah.
Is this supposed to be
Gaussian?
Yeah, but on that side it's also yi.
Here?
No. Like just if you start on the left hand side, you start yi proportional to, and then in the exponent there's yi again.
Oh, okay. So I should actually have been a little bit more clear. So this is the notation that y of I follows. It's not proportional. It follows a normal distribution. So this is a little bit sloppy notation. So in statistics, this is meant to indicate that it follows the distribution. So that means that this is equal to P of y of I given a beta. That's the probability distribution. So when I wrote this up here in the very beginning, when I wrote this, what you see here, that means that epsilon follows a normal distribution. Yeah, it's a little bit sloppy notation. Sorry, my handwriting is not the best one. Okay, so if you now admire this equation here, and you look at the optimization problem, so when we want to maximize or minimize, we take derivatives. So if you look at these equations, instead of this product, because that gives us a little bit cumbersome mathematical expression to deal with, how could we replace this product and obtain something which is easier to compute the derivative of? Take the log, right? So we can replace that function with the log of the function, because then we change the log into a sum. No, the product into a sum. That is equivalent to, so if we can maximize this function here, then we would take the derivative of all these ugly products. But this is equivalent with taking the log of the probability. So that gives us exactly the same equations. So we are going to, or it gives us simple equation, but it's an equivalent problem. So instead of optimizing the product, we now calculate beta argmax of beta, and then we take the log of this function here. Now the log is a function which is a rising function, and it's going to be in this case, a concave function. If we put a minus sign in front of it, then this is going to lead to a minimization problem. And you can show that when you look at the properties of the log. So alternatively, or since we often like to minimize instead of to maximize, we could take argmin of beta epsilon, no, in this domain of minus log of P of D of beta. And these are equivalent problems. And in this specific case, what we would have then is that we get, if we now take the log of this, we would have a sum now. So this is going to give us a sum over all the probabilities. So we would have a sum minus of I equals 0 to n minus 1. And then we have, if we go back to the equation here, we just get a constant, which is now going to be this constant 2 pi sigma squared. And this is going, so we would have a minus, and there is a minus a half, which comes from the log. So that becomes plus. So I would get the log of 2 pi sigma squared, like this. And then we go back. So we have, and we have to keep in mind also that we have a minus in front here. So we have, this gives a minus, a factor of a half. and then I have log 2 pi squared. So this should be a factor of a half here. And then I have a minus and a minus, so that becomes plus. And then when I take this one, I have a minus, multiply with a minus, so that gives also a plus. So I get plus. And now I have, when I take the log of the exponential, this simply gives me y of I minus x of I beta squared divided by 2 sigma squared. No, because I took the log here, and I have the log of this quantity. Yeah. So that gives me simply log of that quantity gives me minus a half of log.
Yes, but we still have the minus in front of our.
Oh, sorry for that. Thanks. Yeah, I didn't see that. Now, the first term is just a constant. So we can actually rewrite this now in terms of a constant. So this is simply a sum over n. So this has been an n half log of 2 pi sigma squared. And then I can just rewrite the second term as plus. And then I just rewrite this in a more compact way as we've done before. And this is the norm 2 of this quantity, 2 sigma squared, norm 2 squared here. And if you now take the minimum, now we take d beta. So this is the function we want to optimize. So when we take the derivatives, with respect to beta, then we just recover the standard equation we had before. So this is the statistical derivation of ordinary least squares, because the function which you see here is exactly the one which we defined as a mean squared error, except that we didn't have the 2 sigma squared. Does that seem plausible? So this is essentially what we had before. So when we take the derivative with respect to beta, this simply leads to what we have seen before. It's going to give us a beta, which is going to be given by x transpose times x minus 1 of x transpose times beta. Okay? Because the mean squared error, just to remind you of that, the MSE was nothing but 1 divided by n. And then we had a sum over I equals 0, n minus 1, y of I minus x of I or beta squared. And we rewrote that one as 1 over n. And then we had y minus x times beta. And then we had the norm 2 here. And what you have then, when you look at the term you have in here, this one, except for the 2 sigma squared, is the same as we had here, except also that we don't have the 1 over n. And when we take the derivatives and want this to 0, then the 1 over n disappears, and the 2 over sigma squared is something we can multiply away. And then we simply have the same term which we had before. So we can derive, have you seen this derivation before? So you can actually make an assumption about the distribution of the variables y given by a normal distribution. And this is actually what Gauss did. So Gauss did the linear algebra piece, with which we started with, and Gauss did also the statistical interpretation. And this was done together with other, I think Laplace was, I think it was one of the other famous mathematicians which derived these results independently, roughly almost 200 years ago, 1850 something. So this is actually very neat because you can make an interpretation in terms of probabilities. Okay, so what about ridge and lasso? Can we make something like that here as well? So in order to do that, we need something which is called Bayes' theorem. And let me just quickly introduce Bayes' theorem for you. So what we are going to say now is the following. We are going to make an ansatz about the probability for beta. And let's see how we can do that. So we are going to make here, an ansatz. And in the statistics language, this is called a prior, for those of you who are familiar with Bayes' theorem, about the distribution of beta. And this is actually something which is going now to lead to the derivation from a statistical point of view of lasso and ridge regression. So I'm doing this because hopefully this can bring up some kind of intuition about what these methods actually mean. So when we do ridge regression in ridge, then there's going to be a probability P of beta, which is going to be equal to a 1 over 2 pi. And I'm going to call this for a variance gamma squared of E to the minus. And then I'm going to have the parameter beta squared. So it has mean value 0. And it has a variance gamma squared. So if I make such an ansatz about the probability beta, I'm going to be able to derive ridge regression. But that, in order to show you that, I need to introduce Bayes' theorem. So if I do lasso, on the other hand, I'm going to make an assumption about this probability for finding beta, because when we did ordinary least squares, we are actually assuming that beta follows a uniform distribution. So that means that all the betas are equally likely. Here, we have another famous distribution. So this is, let me just write it as proportional with, so I don't mix in. So this should be proportional with E to the minus the absolute value of beta divided by, sorry, I think it's 2 divided by lambda. Sorry. This distribution has also a famous name. Has any one of you seen that distribution before with the absolute value? I think this is called a Laplace distribution. So this is just the first one is just a normal distribution with 0 mean value for beta. And this is called a Laplace distribution. So what we need now is something which is called Bayes' theorem in order to do these calculations. And I need to bring back some statistics for you. And there's something in statistics which is called the product rule of probabilities. In order to derive it, it's called probabilities. So I'm just stating some of these. So if I have the probability of finding A and B, so this is actually the union of A and B. This is given as the probability of A given B multiplied with the probability of having B, which again is also equal to the probability of B given A multiplied with the probability of A. So these are typical axioms you will find in statistics text. I got some crumble here, which is just irritating. Okay. I shouldn't have eaten my sandwich before I started here. Then we have something which is called the conditional probability. And the conditional probability is now just taking one of these quantities. So if I take probability of A given B, so what is the probability of A given B? Like we said, what is the probability of Y given beta? If you just take the product rule, this is simply given by the probability of having A and B. So that's the union of A and B, divided by the probability of B. And this is clearly if P of B is larger than 0. Or you can have B given A, and that's given by P of A and B, divided by P of A. Again, if P of A is larger than 0. I should also say that the probability of A and B, if you have independent and identically distributed events, if A and B are IID, then clearly this P of A and B is just given by the probability of A multiplied with the same probability, so the P here now are the same. So they are identically distributed. So if these are identically distributed like we did when we put up the model for ordinary least squares, then this follows from the fact that they have the same distribution here. So if I now combine, there's something which I also need to bring in, and that's called the marginal probability. Let me just give you this final element, the marginal distribution or the marginal probability. So what I'm going to do then is I'm taking my P of A, and I can define that by normalizing. So if this is a continuous distribution, that will be an integral where I integrate out 1 degree of freedom. So then the marginal probability is a probability which is then described only in terms of one of the variables. This is often the kind of probability we would like to have because we just want to deal with one type of variable. So this will be now the sum over all the probabilities of A given B equal to one of the small b's. That's a specific event for B, times the probability of B equal to B. Alternatively, you would have a P of B equal to the sum over A, and then we have the probability of having B given A, and then we are simply summing or integrating away all the degrees of freedom related with one of the variables. So these are just some of the kind of basic statements which you will find in most statistics textbooks. And if you've taken the first course in statistics, these are actually basic statements which pop up there. Now you can combine the product rule with the marginal probability and the conditional probability, and then you can actually define, if you combine these quantities, combining, then we have what is called Bayes' theorem. So the proof of Bayes' theorem based on these probabilities is trivial. It's actually just a straightforward use of these probability definitions. And what it says is that we can rewrite P of A given B is equal to the probability of A and B divided by the probability of B. So this is one of the way of writing it. And this is now given by P of B given A, and P of A divided by this marginal probability. So where we now sum over all, we get rid of the probability A. So this functions as a normalization constant. So this is the way you read this now is as follows. What is the probability of finding A given B? This is now given by the probability of having B given A multiplied with the probability of A divided by a normalization factor. So the quantity you see here is normally has a name in the literature. This is called a likelihood function, and it doesn't need to be normalized. This is called a prior, or what you might call your bias about the system. And the final one, which you have here, this is called the posterior probability. So what we are going to do now is the following. Using Bayes' theorem, we can find a probability for beta given a domain of events. So we could now ask the following question. What is the optimal beta given which describes a domain of events D? Given a domain D. And then we can use Bayes' theorem, where we now can say that we want the probability of beta given D. And this is going to be proportional. And now I'm just going to take away the normalization constant. So I'm going to have D given beta multiplied with the probability of having beta. And this is where you make models. This sounds like a kind of tautology, because you start with a given model and then you end up with another model. But the whole thing now is that if we go back to what we had, this is something we have assumed is given by a normal a Gaussian distribution for the output Y. So this is something which we assumed was a normal distribution with X of beta and a sigma squared. Now, if P of beta is a uniform distribution, what should the final distribution for beta be with a given D? Any good suggestions? If P of beta, this prior, you're now making a model, right? If that is a uniform distribution, what should the final probability of finding beta with a given D be? Yeah. Yes, which is a constant, right? A uniform distribution is 1 over some constant. So you see now that this is going to give us ordinary least squares. And we are going to see this next time when we meet, which should be the 12th of the, we're going to try to meet on the 12th of December. I'm going to send you the time. If I now replace this one with a Gaussian with 0 mean value, I'm going to, when I optimize the probabilities, I will get ridge regression, the same equations as we derived before. If I replace this ansatz with a Laplace distribution, I will get lasso regression. So you can derive these methods using Bayes' theorem with an assumption on the probabilities. So we are making a model for this one. This is a likelihood. This is called a prior. We have a belief that these betas follow a specific distribution. With that, we can make the final question, which is, what is the likelihood of a given beta with that specific output and input D? So you have a data set, and then you're asking the question, which is the beta which fits best the data. And what this probability then represents is actually this. Which beta is the one which is going to fit my data best? And then I'm actually finding a probability distribution for the betas. So if I do ordinary least squares, this is just going to be a constant. So my beta with ordinary least squares is going to follow a normal distribution or Gaussian distribution. And then you can ask yourself, what is the probability distributions if you now make a different ansatz about these probabilities? So keep in mind, this sounds like a game of words and probabilities. But the thing is that in many cases, we have to make an ansatz about what the distribution looks like. And then when you compare that with your data, you can then see whether this fits or not. So this is how you would use Bayes' theorem in actually deriving lasso and ridge regression. And then we will see that when we meet again on the 12th. I just wanted to wrap up this topic because this also has some consequences for how we can interpret the lasso and ridge results when we tune this hyperparameter. And what you're going to see then is that the hyperparameter we had, this lambda, is going to be inversely proportional with the variance, which we assume for the parameter beta. And that gives a nice statistical interpretation about what these hyperparameters are doing. So when we come towards the end of the semester, then we are coming back to this in terms of Gaussian processes, which is a specific way of implementing Bayes' theorem and doing Bayesian machine learning, except that then everything is Gaussian. That's the name, Gaussian processes. That's a very popular method in, for instance, particle physics, in order to describe responses from detectors, for instance, assuming the world is Gaussian. I see many question marks in the faces here. So I'm going to let this go in a little bit. That textbook, which you will find about from Bishop, uses this kind of statistical interpretations all the time. So in many textbooks on machine learning written by statisticians, this is the kind of approach which people would normally use. By the way, there's a legend how Gauss actually came up with the Gaussian distribution. Have you heard of that? I don't know whether it's true or not, but it's a fun story. So many of these mathematics professors at the University of Göttingen, where Gauss was, they were normally a little bit older than their wives. This was quite normal. I mean, old farts marrying young ladies. So the wives would typically be 30 years younger. And the university was worried that they would go bankruptcy because they would have to sustain with their pensions the wives, right? And they would live 30, 40, 50 years more than these old farts who would pass away at the age of 60, 70. So Gauss was actually tasked with seeing whether the pension system of the University of Göttingen was sustainable. And then he looked at found this Gauss, or this distribution over ages, the age distribution, which follows this kind of bell-shaped curve, which gave rise to the Gaussian curve and the Gaussian distribution. That's a legend. I don't know whether it's true or not. I was told this by a statistician. Okay, guys. Then I'm going to send you an email about when we meet next time. So I will be away next week. So I don't want to record the lectures. I thought it's better to have this kind of in-person meeting because then it's more fruitful with questions and everything. Okay, guys. Have a good